Welcome back to the UAV Understanding Drone course. Now in this lecture, we will learn about the components which are used when designing a drone. Drones can be customized for any specific application. The very first step to designing a drone is to educate yourself. This includes learning how flying becomes possible, different associated terminologies, and what impact do various components, the center of gravity and weights, have on the flight of the drone. Besides, there are many drone development platforms and kits that are also available commercially to assist you. When designing drones, not only weight but size also varies from small to large based on the requirement. As discussed earlier, drones come into different configurations, and the cost of the drones always depends on their functionalities and application. Choosing the appropriate is crucial to building a drone with desired specifications. Frame. A frame is the basic skeleton of a drone for attaching all other components as well as providing protection. Commonly known configurations include tricopter 3 arms, quadcopter 4 arms, hexacopter 6 arms, and octocopter 8 arms, and so on. Each arm is connected to a motor. The frames of the quadcopters are usually classified into 3 categories: H, X, and Plus. In X configuration, motor distances are the same side to side and back and front. The advantages of having an X configuration is it gives room to mount stuff, it's very agile, very balanced, and has good aerodynamics and also has better pitch stability. In general, the head structure is more practical if it is intended to locate equipment of a certain size and weight. In fact, it is adopted in a good number of commercial quadcopters. Commercial frames with built-in carbon fiber usually adopt configurations in X. The configuration in Plus is probably the least used. In this case, the frame coincides structurally with the frame in X. That is, with the frame in X, you can choose a configuration in X or in Plus, but the control and the maneuvering procedure is modified. It is enough to observe the figure in order to realize that the pitching movements will be realized by decompensating the lift produced by the front and rear engines only, and that the roll movements will take place when the decompensation takes place on the lateral motors. Without entering into complex aerodynamic considerations, it suffices to consider that the forward and backward and lateral displacement movements will occur because of the lift differences only produced by the two motors, whereas in an X or H configuration, they will occur by the difference of thrust of the 4 motors. It can be said, therefore, without more complex analysis, that this configuration is less efficient. Motors. Motors generate force to rotate the propellers and move through the air. The more efficient the motor, the longer the battery life and hence the flight. All motors should have the same thrust rating, usually given in grams, for ensuring stability. Always check for kV ratings in specifications. If you want the motor to spin faster, choose a motor with a higher kV rating. Usually, a larger motor with a lower kV rating has better efficiency and stability than a smaller one with a higher kV rating. In large drones, brushless outrunner type motors are used, while in smaller, inexpensive models, brushed motors are preferred. DC brushless motors. Brushless motors are considered to be more efficient in terms of performance and operation as opposed to brushed motors. They have all the characteristics required for great drone design: high efficiency, wide speed ranges, and overall high speed torque capabilities. Propellers. The analysis of the components of the quadcopter will be started by the propeller, since in fact it is the most important element for a multi-rotor team. Each propeller is a rotatory wing. The propeller is responsible for converting the power supplied by the engine into useful power for the flight. It is formed by a set of aerodynamic profiles similar to those presented by the wing of an airplane and with a variable angle from the center of the propeller to the tips. If you look at a propeller like the one in the following figure, you can see that the torsion angle of each blade varies from the tips towards the center. It is smaller at the ends and more pronounced at the center. This shape adopted by the blades is due to the fact that the lift produced by an airfoil is proportional to its relative velocity of movement with respect to the air. Therefore, it is considered that at the ends of the propeller, where the radius is greater, the linear velocity of the profiles located in that region is higher. It is evident the need to reduce the torsion, that is angle of attack of the propeller. In a quadcopter type helicopter, a pair of propellers, type puller and other pusher types are required. The names refer to the direction of rotation that the propeller must perform to generate a pushing force in favor of the flight of the vehicle. A series of forces acting on any propeller is shown in the figure and must be known. The torque that turns it A, the thrust produced by it is C, and the resultant of the composing is AB. Battery. In the early days of electric modeling, the only available batteries were nickel-cadmium batteries. Its weight was high, its energy density is low, and its capacity of limited discharge. The advantage they presented was enormous strength and durability. Subsequently, nickel-cadmium batteries with considerably high capacities were used, but the intensive charging and discharging processes in this type of battery are strongly exothermic, and the number of life cycles remained low without having improved the weight problem. Towards the end of the 90s arrived the first batteries of lithium polymer of the mark Cocum arrived in Spain. The batteries came in individual cells and the assembly had to be done manually. Its energy capacity was much lower than the current capacity and its discharge capacity was about 15 times lower. LiPo battery packs that are used in both modeling and industrial applications are made up of sets of cells connected in series or even in parallel series combinations. Each of the cells have a nominal voltage of 3.7 volts, although at full load they reach 4.2 volts. Their discharge depth, that is the minimum value of the voltage they can reach during use, should not fall below 2.8 volts. Use a battery with a higher capacity for more flight time. But remember, higher capacity means more weight. When starting, a maximum flight time of 15 to 20 minutes is suitable. The battery's voltage must match that of the motors. Power distribution board. This is the main element of unmanned aerial vehicles of the multi-rotor type, which is responsible for distributing the power of the power system between the different motors. This board is a printed circuit capable of withstanding high levels of current that has a series of ports in which the different elements are connected. There will be a port in which the terminals of the battery will go through. Of the internal circuit of the plate will be connected to the power outputs of the same, whose number will depend on the number of rotors that own the aircraft. The plate, as its name indicates, is responsible for distributing the power but does not have any element to know how to do it. It is the drive associated with each motor that it is responsible for requiring adequate supply of the battery in each moment in line with the orders received from the flight controller. If a motor has to rotate faster to perform whatever the movement, the inverter connected to the distribution board will be in charge of letting the necessary power to the winding of the motors so that it turns at the desired speed. The distribution plate must be able to withstand the nominal current flow rate when all motors require maximum supply, leaving a safety margin to avoid possible breakdowns. This value is given in amperes and must be powered by the manufacturer. Here I would conclude this lecture and continue with the components in the next lecture.